Good afternoon, everyone, and welcome to my presentation. And today my topic is estimation of cell vitamin A level by color change of pupil in Japanese black cattle. Maybe as you all know that cattle group's objective is to estimate vitamin A level by observing the change of the cattle's eye to produce high quality beef. Today I only focus on the color. This is the outline of my presentation. In background, I will introduce the vitamin A deficiency may cause the change of pupil color. And our objective is to estimate vitamin A level by the change of pupil color. And device is 260 camera. And the method is investigating color change. And also do multilinear regression analysis by using the color factors. Here I show two images of the cutted eyeball, and the comparison between healthy cattle and the cattle suffering from the vitamin A deficiency. So in the right side, that cattle, you can see there are mainly two kinds of difference. First is papilledema, that is a swell of the optic nerve. You can see obviously different from the left side. The other difference is bleached of the tapetum. You can see the color become from the left side yellow color, from left side blue color changed to yellow and some reddish. So they conclude that the vitamin A level, when vitamin A level becomes lower, the blue part of the eye ground will become red or yellow. So our hypothesis is that we can observe this change from outside. That means if we see the pupil color can be affected by the background, the tapetum color. Based on this hypothesis, we do our experiment. And here another literature also compares the normal tapetum and the vitamin deficient tapetum. Compared in the right side, you can see that when low vitamin A level can cause the increase the tapetal reflectivity and the loss of pigmentation. You can see here it's very dark color, but in this part it is a mottled appearance. That means the loss of pigmentation in this area. Another literature is that vitamin A deficiency can cause retinal atrophy. It means here, please show, see here. This part is the tapetum, and on the tapetum that is a retina layer. When retina atrophy happened, so this layer becomes thinner, so less light can be absorbed by the retina. So in other way, that the reflectivity will get higher. We conducted this experiment from 2010, and in that year's result, we found a negative correlation between the red component ratio and vitamin A, and a positive correlation between the saturation and the vitamin A level. In 2011, we conducted the anatomy experiment. We cutted the eyeball of normal cattle's eyeball and vitamin deficient cattle's eyeball, and we found a higher tapetum reflection value in vitamin deficient cattle. So our objective is to estimate the vitamin A level by analyzing the color change of cattle's pupil area. We want to find an alternative to the blood assay. The animal we used include 24 cattle in this presentation, and the cattle's age was 14 to 16 months old at the beginning of the experiment. The period conducted from May in 2011 to December at Hyeogeo Prefecture Hokubu Agriculture Institute. This graph shows the vitamin A change in the experiment period. So it is clearly shown that from May to December that the serum vitamin A level is decreasing, and the institute provided a critical vitamin A value, and it is 30. So at the end of the experiment, all the cattle's vitamin A level lower than 30 international unit per liter. The device we used shown here, and it is based on the 2CCD camera. 2CCD means it can take both color image and near-infrared image simultaneously. And in the mid part, there are light sources, two kinds of light sources. One is near-infrared LED and one is white LED. If you see from the front, you can see the two ring-shaped LED light. And it's connected with a plastic tube to reduce the environment noise, environment light. And because we want to see the tapetum color, so we want to reduce the specular reflection. So we added a PL filter in front of the camera lens and also in front of the white LED light. The experiment procedure shown here. So first we fix the cattle's position, and then we cover the cattle's eye with black cloths. Then wait for 2 minutes for the dilation of the pupil. And then we put the camera in front of the cattle's eye and adjust the camera position by checking the near-infrared image. At this time, the pupil will not shrink. And then turn on the white LED light and record the color images. Then we analyze the image in Visual Studio 2008, and the programming process is the processing process is like this. And first we read the image, both image, color image and the near-infrared image. Because we added a PL filter, so the boundary of the pupil area is not so clear. So we use near-infrared image as an assistant to get accurate pupil area. We do banalization using red, blue value and hue and IR value, and then reduce the noise and detect the halation part, and select the region of interest. This is the pupil area we want to analysis, and get the RGB value, and we evaluate our result in RGB color space and HSI color space. So this is the parameter we extracted from the image. The red component ratio, it is the calculation is like this, and this is for RGB color space. And for HSI color space, because there are some different HSI color model, and we use this triangular pyramid model, and the range of the value HSI is in this range. So to compare with the previous result, I show the previous result in the left side. So in 2010, we conducted the same experiment from July to November. In this period, you can see when vitamin A decreasing and the red component ratio is increasing. Because in this graph we cannot see individually, so to compare the actual change, I plotted the 2 months, 2 experiments data, that is at the beginning of the experiment and at the end of the experiment. So the dark dot is at the beginning of the experiment. You can see all the cathodes red component ratio shift to upper side. So it means small r has a negative tendency with the vitamin A level. So here is the result in 2011. So it is clearly shown also that this negative tendency time series in the time series graph and in this scatter plot also. The individual correlation coefficient is calculated and it shows the small r and the Q value has a higher correlation with the vitamin A level. The scattered plot also shows this tendency. This can be explained that the increased red component ratio shows a color change as the first image I shown. And the decreased saturation can indicate the hyperreflectivity of the tapetum when vitamin A deficiency happens. And I tried multilinear regression to estimate the vitamin A level. Y is at vitamin A level. And first I use color factors, right and small r, small g. And then the coefficient of determination is 0.67. Because in this model, I didn't consider the initial vitamin A level when we introduced the cattle to the feedlot. And in the next model, I included the initial vitamin A level at the beginning of the experiment. And so you can see the improvement of the model. To evaluate the model, I use root mean square error for calibration and prediction. And to compare the two results, and if added the initial vitamin A level, the error becoming smaller, and the coefficient of determination also increased. This is the comparison of the measured value and the estimated value. This is the first model, RG model, and this is added the initial vitamin A level. Then the discussion part. So the error now is about 8 IU per DL. It's still large. And to make the estimation more stable and accurate, it's better to combine other features related to vitamin A deficiency. And conclusion, and the negative and positive correlation between small r and vitamin A and S and vitamin A in 2010 was confirmed in 2011. And the R square value for calibration and prediction is 0.72 and 0.7674 relatively. And thank you for your attention.
You didn't put Tangawa-san yet?
No,
Not yet.
not yet.
Now doing it.
Yes, now doing.
In slide 13, when you have your correlation and you show your correlation, if you use this correlation to try and predict critical vitamin A level in the cattle, how many cattle would you have accurately predicted that their vitamin A level is critical?
Actually, I did not do this analysis, but maybe we can see in this graph. So to measure the vitamin A level, under 30. Under 30. So if this dot is under this line, so maybe it is accurate predicted. So actually 3 out of 1, 2, 3, 4, 5, 6. 3 out of 9. Only 30%. But in this model may be better. But in current case, maybe 30%.
So having a demonstration of how accurate your prediction is to date will also give the audience some value of, is 0.73 already good enough, or how far do you have to go before it can be used in a commercial situation?
I see. Actually, there are no standards, so maybe that in that way it's better. It's easier to understand. I see. Thank you.
Any other? Okay. Before you mentioned some variables, or some candidates of variables, such as R, GB, and also SI. And then how you select this? Only use R and G?
Because currently the parameter calculation here, so in this formula RGB is highly correlated, so every 2 can represent the whole value. So I selected RGB. It is same with R and B. And for HSI, because H and S can be calculated from RG, to prevent overfitting, I only use the RGB.
So
but in this calculation, yes, we didn't add the intensity value because this is normalized red component ratio.
So you did not some statistical analysis to select which parameters actually highly influence your vitamin C, your vitamin A.
Actually, in this parameter, only this 2 is effective. So if you evaluate, compare R and G, so small r is most highly correlated with. Small r is higher than small g.
No, I mean this correlation you calculated one by one independently.
Yes, independently.
But I think the story will be different if you try to RGB and SI is how they interact to your vitamin A, and then by some statistical analysis you can show us if we deselect this.
You mean different combination? Do you mean
yes,
different?
Yes, like that. Or some maybe, for example, in some statistical analysis they use some effect analysis to see which parameter is highly or give a significant effect to your vitamin A.
Thank you for your suggestion. I I will try.
Anyone else?
Very simple question. I'm not familiar with the cattle, so I have a question. As the age how in case of humans, very young boys have a white eye. On the other hand, as a person, in case of older man, have a little yellow or red eye.
Uh,
So I think age have an effect. In your
but
result, maybe you can consider the result of the other time at the same
yes, it's a defect of this experiment. Now we don't have the control group in this experiment, so we cannot determine this is really caused by vitamin A or caused by age. So we should include the control group. That means no vitamin A control group to compare. So maybe we can know if age has effect or not.
For example, in this graph containing the other time of data.
Yes, but all the cattle, the vitamin A level is decreasing, and also the age is increasing. So age, vitamin A, simultaneously affect the color, so we cannot. No. Thank you.
Do you have some data, lens reflect that's transmittance?
Yes, we have some data on lens, but that data is a comparison between 1-year-old cattle and 10-year-old cattle. But in current vitamin controlled period, it's just a short period. It is only 8 months. So in this,
some lens get color change or almost same?
we don't have enough data, and we compare the 1-year-old cattle and the 10-year-old cattle. The lens become yellow in 10 years old cattle.
Hopefully, we'd like to see those data. And finally, when you analyze MLA, you may put another different type of data, that is body temperature or some weight, or some, if possible, some cattle's behavior. How many times drink water in the one night? Those kind of, yeah. Actually, we would like to
Yes.
some diagnosis.
I think if we added more factor, it will be more accurate.
Probably more accurate. As possible.
Yes, I see.
Why you use MLR for this? I mean, R, G, R, small g, small b, S, I, all is color information, and each other has correlation.
For example, the small r and s is highly correlated, so you can see this value is same.
So I think traditional MLR is maybe not good for if you have such kind of variables strongly correlated. So if this is as maybe mentioned by Sensei, if you have another information that is maybe highly different with this parameter, it should be okay for MLR. But if you have such kind of highly correlated variables, why not use such PLS? PLS can handle such kind of highly correlated variables. They will decompose to.
But HSI was calculated from this three.
Yes, that was very high.
Yes, but
So using MLR.
but I didn't use that, so I only use RG.
So R and G is different.
R and G, of course, is different.
His suggestion is how about the PLS using?
Because you have many information from this R, G, V, so why use? Yes, try it.
I will try.
And we are interested to see what is the result.
Maybe better.
Okay.
PLS is more than 2 is multivariate.
But currently only 2, so I will add it more.
It has 6 variables. That is
You combine Tanigawa-san data and shrinking data. You have many data. I think it's time to stop talking. Okay, thank you very much.